Hey everyone, so today we're going to be working on some more applications of linear equations, some word problems here. So one really important equation we're going to be using today is distance equals rate times time. Distance equals rate times time. One way that we can see that this actually works, if you think of a common rate, time, and distance, like let's say miles per hour. So if I had miles over hour and I multiplied by, this is a rate, and I multiplied by hours, which is a time, you would cancel these out and I would just get miles, which is a distance. So that is where distance equals rate times time is coming from. So I just wanted you to clarify that. I know sometimes you guys do something like this in bio or chem. So important one for us, and we're about to use it. So the first problem here we have, on a vacation trip, Jake averaged 50 miles per hour going from Denver to Minneapolis and returning by a different route that covered the same number of miles. He averaged 55 miles per hour. So what's the distance between the two cities if his total traveling time was 32 hours? Okay, so what we want to do for this, and typically what I do, is I kind of set up a little table here. So I'm going to set up this table. We can use our nice little notability shapes here. Oops, I kind of want it to be a rectangle. There we go. Okay, and I'm going to make this into rate times time is equal to distance. Rate times time is equal to distance. Anything that's a rate is going to go in the first column. Anybody that's a time is going to go in the second column, and the distance is going to go in the third column. Now, we have kind of two routes here. First, he went from Denver to Minneapolis, and then he went from Minneapolis to Denver. So those are kind of my two rows here for my table. So let's start reading here. We want to read, and as we're going, think about the types of units, guys. Miles per hour, that's a rate. Okay, so 50 miles per hour, that was from Denver to Minneapolis. That's going to go right here in rate. All right, what else do we have? Returning by a different route that covered the same number of miles. So this is important here. Okay, I'm going to write a little note that distance is equal, because sometimes it's not. Okay, the distances are equal. He averaged 55 miles per hour on the way back. What is the distance between the two cities if his total traveling time was 32 hours? So I want you guys to think about this. It's a little bit difficult because a lot of people want to do something like this. Like some people are like, oh, well, maybe it just means that he went, I don't know, could you just guess, like 16 and 16? Well, but he went faster, right, on the way there. So we cannot just guess 16 and 16. We cannot do like x and 32, right? Because that means it only took him 32 hours only for this side. We want it to be total. So what we're going to do, okay, is name one of them x. We can name this one x. If that took him 10 hours, then this is going to take him 32 minus 10 hours. Okay, so when you have a total time, you want to name them x and then the total minus x. Like again, like I said, if this was 15, and then you did 32 minus 15, this would be 17. So that would add up to 32. Okay, so we don't have any more information about the distance, but we can say that rate times time is the distance. So 50x is the first distance, and the second distance is 55 times 32 minus x. Now, I wrote a little note to us, and that's going to be really important here, was that the distances were equal. Okay, the distances were equal. His distance on the way there, his rate times time, was equal to his distance, or his rate times time, on the way back. Now you could switch. This could be 32 minus x, and this could be x, just as a heads up. We'll get the same answer in the end. So that's what we're going to do for distances are equal. Basically, you do rate times time is equal to the other rate times time. It might be two different like planes traveling the same distance. It could be the same person going back and forth, like this situation. And then we're just going to solve for x. So we get 50x equals 1760 minus 55x. 105x equals 1760. And so x is equal to 16.76 hours. Okay, now, as you guys get that answer there, and you can use a calculator, 16.76, is that my final answer? I move on. Well, careful. It said, what is the distance between the two cities? It should be the same no matter where I plug it in. And if I'm plugging into a distance, then I want to plug in, for example, one of the distances was 50 times x. I could also do 55 times 32 minus x. And I should get the same answer here if you plug it into a calculator, and you end up getting the distance is 838.095 miles. Alrighty, guys. So we're going to try a couple more scenarios here to see some different distance problems. That was one where the distances were the same. Okay, here's a situation where the distances are not going to be the same. So, for example, Mrs. Denna and Mrs. Sager are running along Lake Michigan. Mrs. Denna runs at 6 miles per hour, where Mrs. Denna only runs at 4. They start at the same time. How long will it take before they're a half mile apart? So I want you guys to think about this one. Okay, are they running the same distance? No. So I would write yourself a little note and just say distances are different, right? So we're not going to be setting the distances equal. And one other thing I want you to think about is if they're running in the same direction, what does that look like? Well, if I was running in the same direction with you and, I was running really fast, I'm obviously faster than you, and you were running right behind me, okay, and maybe you ended up here, how are we going to find the distance apart? We're going to end up subtracting, okay? So if we're going the same direction, important note here, if you're traveling the same direction, you're going to subtract the distances. Okay, let's say if I was running really fast going, east, and you were running really fast going west, well, then to find our differences, or to find our distance apart, if we're going opposite directions, you can just write yourself a note. We don't need it for this one, but opposite direction, we would be adding the distances. Okay, if I ran 5 miles this way, you ran 3 miles this way, we'd be 8 miles apart. But if we're going the same direction, such as 5 and 3, then we'd be subtracting. We'd only be 2 miles apart. Okay, so there's some important notes on that. So let's set up that same table. Pause if you need to. Write down those little pieces there. Same direction, we're going to subtract the distance. Opposite directions, we're going to add the distances. And when we create this little table, again, it's the same as above. So we know this is a rate times time problem because we're talking about distance, we're talking about miles per hour, etc. Okay, so I'll say Denna versus Sager are my 2 rows here. And I was given some information, right? I was given Mrs. Denna runs at 6 miles per hour and Mrs. Denna is 4 miles per hour. Those are both rates. Okay, and for time, okay, we know, are the times the same, different? Did we give a time? Well, it said if they start at the same time. So technically, it's just some time t, or you could say x if you guys like that better, maybe. So they run the same amount of time. You start the clock and you end the clock at the same time, so x. Okay, so Mrs. Denna's distance would technically be 6x, and Sager's distance would be 4x. And again, if she's running 6x and she's running 4x, and we want to know when are they a half mile apart, that's the ending here, okay? That's just going to be the equation. We just mentioned this. 6x minus 4x. Rate times time minus rate times time is equal to the distance apart. So equal to 1/2, or 0.5 you could say. Okay, if we solve this out, we get 2x is equal to 1/2. If you divide by 2, you get x is 0.25. This is in hours, since we are in miles per hour. A quarter of an hour is also 15 minutes, so I would take either of those answers. And that is the final answer here because it said, how long will it take them? So I found x, which I represented with time. So that's it for that one. Okay, I want to try one more that's similar to that, and then we'll kind of move on to a different type of equation here. So I'm going to save number 3 for class. Okay, number 4, I want to talk about very similar to that running one. Okay, 2 planes leave Chicago at the same time. One heads north and the other heads south. One heads north, the other heads south. This one's going one way, this guy's going the other. When we're talking about their distance apart, we're going to be adding, right? If he goes 50 miles this way, 70 miles this way, they'd be 120 miles apart. So different from what we just did. So if we have opposite direction, we just wrote this down, opposite directions, we're going to add the distances. Okay, now it says, what else? We've got one's going to St. Louis. The Minneapolis plane flies 70 miles per hour faster. In 1/2 hour, the planes are 350 miles apart. What are their speeds? Okay, which also we would know as rates. So let's try this out here. Again, we set up a table. Always my recommendation to start. Rate times time is equal to distance. My first plane is going to Minneapolis, and my second plane is going to St. Louis. And again, I'm just going to try to write down the things that I know here. So let's see. It says 1/2 hour, and that's for both. So I'm just going to write 1/2 here. Now, a lot of people want to write 30 for 30 minutes. People like to write 30 there, and that's going to be a big issue because it has to be in hours. If I'm talking about miles per hour, then this has to be in hours. You could write 0.5, okay, but it has to stay in hours. And then for rate, okay, it said Minneapolis is 70 miles per hour faster than St. Louis. So I would do something like this. X and X plus 70 miles per hour faster. Okay, so we don't know the distance. We're talking about, how far apart are they? We're going to add those distances together. We know they're 350 miles apart. This one is going to be 1/2 times X plus 70. And this one, remember, we're multiplying these together. This one is 1/2 times X. And for opposite directions, we're doing rate times time plus rate times time is equal to the distance apart, because we're going opposite, north and south here. So 1/2 X plus 70 plus 1/2 times X, when are they 350 miles apart? So that was kind of the ending here. All right, so we solved this up. 1/2 X plus 35 plus 1/2 X equals 350. That gives us X is equal to 315, if you don't mind me rooting that. Okay, and again, we have to think, what did X represent? A lot of people answer these questions wrong because they don't understand what X represents. So X represents, right here, the rate of the St. Louis plane, and we want to say what are the speeds in general. So the St. Louis plane was 315 miles per hour, and the Minneapolis plane was X plus 70. So plus 70 here would give me Minneapolis was 385 miles per hour, and that would be your very final answer there. Okay, so hold on to those. Again, number 3 is a different distance problem, so I will do that one with you guys in class. I want to try out, so 5 and 6 are very similar, and then we're going to save 7 for class. So 5 and 6, if you guys join me on those, we're going to talk about one more equation that's really important. This one's about cleaning. This one's about inlet pipes or things that are working. Okay, so another thing we know is work equals rate times time. So W is for work. Okay, so besides distance equals rate times time, we also talk about work. This is like how many houses can I paint in an hour, per hour, how many gallons of water can a pipe add to a pool per hour. That's the work that this pipe is doing, the work that the person is doing. So very similar setup here. It says Tom can clean a room in 3 hours. Sue can clean a room in 5 hours. How long would it take them to clean together? Okay, well, you might be tempted to just say 3 plus 5, it would take them 8 hours. Well, then they became pretty inefficient, right? If Tom was cleaning only in 3 and then he added Sue and now it takes them 8 hours, it's not really a good deal there. So it's actually going to be quicker, right? It should be faster than 3 hours and 5 hours, okay? So what we're going to do is set up a very, very similar table here. Rate times time is equal to work. Okay, and what we're going to do here is just we have to be very careful. So this is going to be Tom, and this is going to be Sue. Now, time, it says they cleaned the same room. How long would it take them to clean together? So technically, they're cleaning for the same amount of time, so I'm going to call that X. It says Tom can clean a room in 3 hours. So I want you guys to think of what could be a rate that you could give Tom. Like if you're like, Tom, you're so good at cleaning. You clean one room every 3 hours or 1/3 room per hour. If you just write, 3 here, well, that's not really a rate. You have to change this into a rate. So I did 1 room per 3 hours. I created a rate. And same thing with this Sue cleaning in 5 hours. Well, she can clean 1 room per 5 hours. Or you could say she cleans 1/5 room per hour. Okay. Now, the nice thing about work is that it always adds up to 1. Okay, because they want to clean 1 room together. So Tom's work is 1/3 x, and Sue's work is 1/5 x. And since they are working together, we're going to say work, or rate times time, plus Sue's work, the work she puts in, rate times time, is equal to 1. Okay, work is always equal to 1. Always, always. And that's the equation we're going to solve. So we can multiply by 15 over 1 to get rid of those denominators. 5x plus 3x is equal to 15. Okay, and that gives us 8x is equal to 15, which is 15/8. X represents our time here. So it would take them 15/8 of an hour, or it's the same as 1 7/8 hour. And this makes sense to us because now it's a lot faster than them working alone. Them working together should be quicker. So 15/8 hour is your final answer. That would be how long it takes them to work together. Now, there is a situation where we might talk about things working against each other. So typically it's not within cleaning. That'd be like if Tom was cleaning and Sue came around and threw all the clothes on the floor. Typically it's for these pipe problems. Okay, so we'll set up this next problem here. The sewage treatment plant one, which is just delightful to talk about sewage. I don't know if you were looking to talk about it, but here it is. Okay, so very similar situation. We see pipes that are working to fill a pond. So we're talking about work here. We're going to be adding, it says 1 fills the pond in 8 hours, 1 fills it in 10 hours. So they're working together. So again, we're going to be kind of doing this rate times time plus rate times time is equal to 1. And we just want to figure out what are those rate times time situations. Rate times time is equal to 1. We'll call that, it's equal to work technically. Let's put that for now. That's not rate times time is equal to 1. And we'll put the first pipe and the second pipe is what I'll call them. Okay. Now, this one, a little bit different here. Hopefully we can come up with those rates. So if I ask you, I say, look back here, it says 1 can fill it in 8 hours. What would you guys say the rate is? How many pools can it fill per hour? Or ponds can it fill per hour? How many ponds per hour? That would be 1 pond per 8 hours, right? Because it can do 1 pond in 8 hours. Then it says the other is 10, so 1 pond per 10 hours. We want to create it to be a rate. Pond per hour. Okay, now for the time. The first pipe is open for 4 hours, and then the second pipe is opened. How long after the second pipe is opened will it take to fill the pond? So this one's slightly different, so just be really careful here. Okay, I always kind of think, who's the original time? Well, it says the second pipe is opened, and how long, we want to know how long is that one open. So I'm just going to call that X. Okay, well, if the first pipe is open 4 hours before that, what could we say for the first pipe? Well, it's 4 hours more than the second pipe. You also could say this, so note to yourself here, you also could do the first pipe is X, and the second pipe is open 4 hours less. So you could do the exact same thing, just switch it to be X and X minus 4. But overall, this first pipe is working harder, right? It's open for 4 more hours, so it should have the extra hours. So I usually add here. Okay, now this one is 1/8 times X plus 4 is its work. This one is 1/10 times X. And again, we're adding those. It says how long to fill 1 pond. Okay, how long does it take after the second pipe is opened, which in this case is X. Okay, for us, right? That's the time of the second pipe. So we're just going to be solving for X here. And we're going to be adding the work together because they're both filling the pond. There's going to be equations that we do or situations where one is filling the pond and one, it might be draining, or maybe you left the drain open of your backyard pool. Then we would have to do RT minus RT, okay? Subtract if it's working against. These are working together, so we've got 1/8 times x plus 4 plus 1/10 times x. That's equal to 1 pond. So the working together for 1 pond. We can multiply by maybe 40 over 1. That would be the LCD of 8 and 10. Okay, and as we multiply through, I would get 5 times x plus 4 equals 4x equals 40. That should say plus, I'm very sorry. So when you multiply these in, guys, just multiply to the front of the parentheses. It will be taken care of when we multiply into the parentheses, only the front of the parentheses. So we just solve this up here. 5x plus 20 plus 4x is equal to 40. 9x is equal to 20. And x is equal to 20/9. Again, we're talking hours here. That is totally fine with me in terms of an answer. You could obviously also write, what is that, 2 2/9. For hours, that also works, but 20/9 is perfectly acceptable. So that is it for the work and distance problems. As I mentioned, so these are the 2 work problems, 5 and 6, okay, where we're adding work together to equal 1 task. Maybe it's painting a room, maybe it's cleaning a room, maybe it's painting a house, maybe it's filling a sewage pond. Okay, we're going to work on this one more type of problem tomorrow called, I kind of call them like chemistry problems. Okay, and besides that, the main thing we started with today, remember, was those distance problems. Distances are equal. Rate times time equals rate times time. If the distances, if we're going the same direction, but different distance, we're subtracting the distances. And if we're going, that was if we're going the same direction. If we're going opposite directions, we're going to be adding the distances equal to the distance apart. So those are the 3 key things from distance. We'll try number 3 and 7 in class. And thanks again for watching. Make sure you guys look through these again. Come in with any questions. These are pretty tough. Have a good night.